astronomers found a wall of galaxies 10 billion light-years wide. According to physics, it cannot exist. The universe is only 13.8 billion years old. There has not been enough time since the Big Bang for gravity to pull together anything this massive. Yet we see it, stretching across 10% of the observable universe. We are going to explore the structure that broke cosmology. You will see how gamma-ray bursts exposed this impossible formation, why computer simulations cannot recreate it, and what happens when the rules of the universe stop making sense. If you are ready to question everything we thought we knew about cosmic structure, hit that like button and subscribe. Let us begin. In November 2013, a team of astronomers noticed something wrong with their gamma-ray data. These bursts of energy come from dying stars across the cosmos, each one marking where a massive stellar body collapsed. The researchers were mapping their locations to understand how galaxies spread through space. What they found made no sense. The gamma-ray bursts formed a pattern. They clustered together across a region so vast that it dwarfed everything astronomers had ever observed. Imagine looking at a map of your city and suddenly realizing all the buildings form a single continuous structure stretching from New York to Los Angeles. That gives you a fraction of the scale we are discussing. The structure measured approximately 10 billion light-years across. To put that in perspective, our entire Milky Way galaxy spans about 100,000 light-years. This formation was 100 million times wider than our galaxy. Light leaving one edge of this structure would take 10 billion years to reach the other side, traveling at 670 million miles per hour. The team ran their calculations again, then again. The pattern remained. They were looking at what appeared to be a connected wall of galaxy superclusters, each supercluster containing tens of thousands of galaxies, each galaxy containing hundreds of billions of stars. The math worked. The measurements were solid. The problem was different. According to the cosmological principle, the universe should be roughly uniform at large scales. Think of it like looking at an ocean from an airplane. Up close, you see individual waves, but zoom out far enough and the surface appears smooth and even. The universe should work the same way. Small variations close up, uniformity at cosmic distances. This structure violated that principle completely. It was confirmed through multiple independent observations using different detection methods. Scientists cross-referenced the gamma-ray burst data with optical telescopes and radio surveys. Everything pointed to the same conclusion. Something disorganized existed where randomness should dominate. The discovery team named it the Hercules Corona Borealis Great Wall. The name comes from its location in the sky, positioned between the constellations Hercules and Corona Borealis as viewed from Earth. But names were the least of their concerns. They had just found something that challenged nearly a century of cosmological theory. Here is where it gets stranger. The theoretical maximum size for any cosmic structure sits at about 1.2 billion light-years across. That number comes from decades of physics calculations about how fast gravity can work and how much time has passed since the Big Bang. Anything larger simply should not have had time to form, yet this wall measured 8 times that theoretical limit. The researchers published their findings knowing the backlash would come. Some astronomers questioned whether this was truly a single structure or just a statistical fluke. Others argued the gamma-ray bursts might be clustering by chance. But the data kept supporting the same conclusion. The probability of this pattern forming randomly was less than 1 in several thousand. Even more unsettling was what this meant for our understanding of cosmic evolution. If structures this massive can exist, then our models of how the universe developed after the Big Bang need serious revision. Every simulation, every equation, every prediction about large-scale cosmic architecture assumed nothing could grow this big. What could pull together that much matter over such distances? Gamma-ray bursts are the brightest electromagnetic events in the universe. When a star at least 20 times more massive than our closest star collapses into a black hole, It releases more energy in 10 seconds than our star will produce in its entire 10 billion year lifetime. These explosions shine so bright that we can detect them from the edge of the observable universe. Each burst acts like a cosmic lighthouse. It tells us exactly where a massive star died and, more importantly, when. Because light takes time to travel, seeing a gamma ray burst from 10 billion light-years away means we are watching an event that happened 10 billion years ago. The light has been traveling toward Earth all that time. Astronomers use these bursts to map the ancient universe. By recording where each explosion occurs, they build a three-dimensional picture of how galaxies were distributed billions of years ago. It is like taking a photograph of the universe in its youth. Most of the time, these bursts scatter randomly across the sky. That is what the cosmological principle predicts. The Hercules Corona Borealis Great Wall appeared when researchers plotted 283 gamma-ray bursts detected between 1997 and 2012. Instead of random distribution, they found clustering, intense clustering. The bursts formed a distinct line across one section of the sky, all occurring at roughly the same distance from Earth. This concentration suggested something massive occupied that region of space. Galaxy clusters tend to produce more stars, which means more supernovae, which means more gamma-ray bursts. Find a concentration of bursts, and you have likely found a concentration of galaxies. Simple enough in theory, but the concentration they observed stretched too far. The gamma-ray bursts mapped out a region spanning roughly 60 degrees across the sky. From our viewpoint on Earth, that is about 120 full moons placed side by side. Now remember, these bursts were all happening approximately 10 billion light-years away. Geometry tells us that something 60 degrees wide at that distance must be monumentally, impossibly large. The team used statistical analysis to confirm the clustering was real. They divided the sky into sections and counted how many gamma-ray bursts appeared in each one. The section containing the Great Wall had significantly more bursts than probability allowed. The odds of this happening by random chance measured at less than 1 in 2,000. Other research teams began checking the data independently. They used different statistical methods. They looked for errors in the original measurements. They cross-referenced the gamma-ray positions with surveys of galaxy distributions. Every analysis confirmed the same thing. The clustering was real. The structure existed. What makes gamma-ray bursts especially valuable for this kind of research is their brightness. We can see them across distances where galaxies become too faint to detect directly. They illuminate regions of the universe that would otherwise remain hidden. In this case, they revealed something we never expected to find. Something that had been sitting in our data for years, waiting for someone to look at the pattern instead of individual points. The cosmological principle states that the universe looks essentially the same in all directions when viewed at large enough scales. This idea forms the foundation of modern cosmology. Without it, our equations describing cosmic expansion stop working. Our models of the Big Bang collapse. Everything we think we understand about the universe falls apart. The principle emerged from observations made throughout the 20th century. Astronomers noticed that galaxies spread across space in a relatively uniform way. Sure, you get clusters here and there. You see voids where fewer galaxies exist. But step back far enough, and the average density of matter stays consistent. The universe has no center, no edge, no special direction. This uniformity comes with a built-in scale limit. Calculations show that structures in the universe should not exceed about 1.2 billion light-years across. That number derives from something called the particle horizon during the early universe. Essentially, it is the maximum distance over which matter could have influenced other matter in the time available since the Big Bang. Think of it like this. Gravity pulls matter together, but it moves at a finite speed. The universe is only 13.8 billion years old. There has only been so much time for gravity to do its work. Even if every particle of matter in a region started pulling on every other particle from the moment of the Big Bang, there is a mathematical limit to how large a structure they could build. The Hercules Corona Borealis Great Wall exceeds that limit by a factor of 8. It is not just big, it is impossibly big, given the age of the universe and the speed at which gravity operates. Imagine trying to build a bridge, but you only have enough time to construct 100 feet of it before your deadline. Then someone points out your bridge is 800 feet long. Either your measurements are wrong, your timeline is wrong, or the laws of physics you are using do not apply. Scientists call this the horizon problem. Different regions of the universe should not be able to coordinate their behavior across distances larger than light could have traveled since the beginning of time. Yet here sits a structure that appears coordinated across 10 billion light-years. How did all that matter know to clump together in the same direction? Some physicists suggested the structure might have formed earlier than we think, during a period called cosmic inflation. Inflation theory proposes that the universe expanded exponentially fast in the first fraction of a second after the Big Bang. This expansion could have stretched quantum fluctuations into the seeds of large structures. But even inflation has limits. The mathematics of inflation predict structures should still cap out around that 1.2 billion light-year mark. The Great Wall sits far beyond what inflation can explain. It challenges the principle that the universe develops uniformly. It suggests that either our understanding of cosmic evolution is incomplete, or we are seeing something we have completely misinterpreted. Neither option provides comfort when you have spent decades believing you understood how the cosmos works. Picture our Milky Way galaxy floating in space. 100 billion stars spinning in a spiral disk about 100,000 light-years wide. That seems enormous from our perspective, standing on a small planet orbiting one average star near the outer edge. But in cosmic terms, the Milky Way is tiny. Now zoom out. Our galaxy belongs to a group called the Local Group, which contains about 80 galaxies clustered within 10 million light-years. The Local Group itself sits inside a larger structure called the Virgo supercluster, a collection of galaxy groups spanning 110 million light-years. Superclusters represent some of the biggest structures astronomers recognized before 2013. The Hercules Corona Borealis Great Wall contains thousands of superclusters. Imagine stacking the Virgo supercluster 90 times in a row. You still would not reach the size of the Great Wall. This structure makes our supercluster look like a single grain of sand on a beach that stretches for thousands of miles. Scientists measured the Great Wall using redshift, which tells us how far away objects are based on how much the universe has stretched their light. Light from the Great Wall has a redshift value between 1.6 and 2.1. Those numbers translate to a distance of roughly 10 billion light-years and an age of 10 billion years. We are seeing this structure as it existed when the universe was less than 4 billion years old. At that time in cosmic history, the universe was still relatively young. The first stars had formed. The first galaxies were coming together. But conventional theory says there had not been enough time for gravity to assemble anything approaching the scale of the Great Wall. Matter was still spreading out, still organizing into the structures we see today. Large-scale cosmic architecture was supposed to still be under construction. Yet the Great Wall was already there, already formed, already massive beyond theoretical limits. The structure contains an estimated 18 billion trillion stars. That number is so large it loses meaning. But try this comparison. If every star in the Great Wall represented $1, you would have enough money to give every person on Earth about $2.5 trillion each. And that still would not exhaust your supply. All those stars mean enormous amounts of mass. Mass means gravity. Gravity means the structure exerts influence over an incredibly vast region of space. Any galaxy wandering too close to the Great Wall gets pulled toward it, eventually joining the structure and making it even more massive. This feedback loop should have limits based on how fast gravity can work and how much time has passed. The Great Wall appears to have ignored those limits completely. Understanding the scale helps us grasp why this discovery shook cosmology. This is beyond an anomaly. This is beyond an outlier in the data. This is a fundamental challenge to our equations, our models, our entire framework for understanding how the universe grows and evolves over time. And it gets bigger when you look closer. When you point a telescope at the night sky and capture light from distant galaxies, you are not seeing those galaxies as they exist now. You are seeing them as they were when their light began its journey toward Earth. Light from a galaxy 1 million light-years away shows you that galaxy as it looked 1 million years ago. Light from 10 billion light-years away shows you 10 billion years into the past. This time delay gives astronomers a powerful tool. By observing objects at different distances, we can watch the universe evolve. We see galaxies forming in the early universe. We watch them merge and grow. We track how cosmic structures developed from the nearly uniform conditions after the Big Bang into the complex web of galaxies, clusters, and voids we observe today. The gamma-ray bursts that revealed the Great Wall occurred between 9 and 10 billion light-years from Earth. That means we are observing events that happened 9 to 10 billion years ago, when the universe was only about 4 billion years old. We are looking back through time to see a structure that had already formed while the cosmos was still in its developmental phase. Here is where the timeline becomes problematic. The Big Bang happened 13.8 billion years ago. In the first few 100 million years after that, the universe was too hot and dense for stable structures to form. Stars needed about 200 million years to appear. Galaxies took several 100 million years to coalesce. The universe needed time to cool, to expand, to allow gravity to pull matter together into organized structures. By the time we see the Great Wall, only about 3.8 billion years had passed since conditions became stable enough for large-scale structure formation to begin. That gives gravity 3.8 billion years to collect galaxies into superclusters and arrange those superclusters into a wall spanning 10 billion light-years. Standard physics says this is impossible. Gravity propagates at the speed of light. Even if two regions of space started pulling toward each other from the moment structure formation began, they could only influence each other across distances. Light could travel in 3.8 billion years. That limits structure size to about 3.8 billion light-years maximum. The Great Wall spans more than twice that distance. Some researchers propose the structure might have started forming even earlier, during the period immediately after the Big Bang, when quantum fluctuations could create tiny variations in matter density. These variations could act as seeds that gravity later enhanced into large structures. Computer simulations based on this idea consistently produce structures no larger than 1.2 billion light-years across. They never produce anything like the Great Wall. The timeline problem gets worse when you consider that the Great Wall is not just large, it is organized. The gamma-ray bursts show a clear linear pattern, suggesting the structure has a defined shape and orientation. Random gravitational collapse should produce more circular or irregular formations. This looks deliberate, which makes no sense because gravity does not have preferences or directions. Something about our understanding of cosmic evolution must be incomplete. Laszlo Balázs led the team that discovered the Great Wall. He is a Hungarian astronomer who specializes in gamma-ray burst research at the Konkoly Observatory. When his team first processed the data showing this massive clustering of bursts, Balázs assumed something had gone wrong with their analysis. The pattern was too strong, too organized, too large to be real. They checked their instruments. They reviewed their calculations. They looked for coding errors in the software they used to map the burst positions. Everything checked out. The gamma-ray bursts were clustering exactly where the measurements showed. The pattern was real. Balázs described the feeling as looking at something that should not exist. Imagine working on a puzzle and discovering a piece that is 8 times larger than the frame supposedly can hold. Either the piece is wrong, the frame is wrong, or your understanding of how puzzles work is fundamentally flawed. Those were the only options. The team spent months verifying their findings before publishing. They used statistical tests to measure how likely this clustering could occur by random chance. The tests came back showing odds of less than 1 in 2,000. In scientific terms, that is significant. In practical terms, that means if you repeated the history of the universe 2,000 times, this pattern might randomly appear once. Maybe. Other astronomers were skeptical when the paper first appeared. Skepticism is healthy in science. Extraordinary claims require extraordinary evidence. Several research groups set out to either confirm or debunk the discovery using independent datasets. They looked at optical surveys that mapped galaxy positions. They examined X-ray data from space telescopes. They analyzed radio observations from deep space. Every independent analysis confirmed the structure. The Great Wall was there. The measurements were accurate. The size calculations were correct. The cosmological problem was real. What made this particularly challenging for the astronomy community was that the Great Wall did not announce itself dramatically. There was no obvious visual signature in the sky. You could not point a telescope at a specific location and see a wall of galaxies spanning your field of view. The structure revealed itself only through careful statistical analysis of gamma-ray burst positions accumulated over 15 years. This meant the Great Wall had been hiding in plain sight in our data. Astronomers had been recording these gamma-ray bursts for years without realizing they were mapping something impossible. The bursts seemed random until someone stepped back and looked at the overall pattern. Only then did the structure emerge. Balazs noted in interviews that discoveries like this make you question what else might be hidden in astronomical data. If a structure this large could go unnoticed for over a decade, what other cosmic anomalies are we missing because we are not asking the right questions or looking at our observations from the right perspective? The Great Wall changed how astronomers approach large-scale cosmic mapping. Teams now specifically look for unexpected patterns and clustering at scales previously thought impossible, and they are finding things that suggest the Great Wall might not be alone. The theoretical size limit for cosmic structures comes from a concept called the homogeneity scale. This is the distance at which the universe should start looking uniform. Below this scale, you see clusters and voids. Above this scale, matter should be distributed evenly in all directions. Decades of observation and mathematical modeling placed this scale at approximately 1.2 billion light-years. That number is not arbitrary. It derives from the physics of cosmic expansion and gravity. When the universe was young, matter was distributed almost uniformly with only tiny variations in density. These variations were quantum fluctuations, stretched to cosmic scales by inflation. Over time, gravity amplified these fluctuations. Denser regions attracted more matter and became clusters. Less dense regions emptied out and became voids. But gravity needs time to work. It can only pull matter together at finite speeds. The universe has only existed for 13.8 billion years. That limits how large gravitationally bound structures can grow. Physics sets a firm boundary on structure size based on these constraints. The Great Wall is 8 times larger than that boundary. Several physicists have proposed modifications to explain this. One idea suggests that the early universe had larger quantum fluctuations than we currently think. Bigger initial variations would allow bigger final structures. The problem is, we can measure those early fluctuations by looking at the cosmic microwave background radiation. The measurements show fluctuations too small to produce anything like the Great Wall. Another proposal involves dark matter. We know dark matter exists because we can see its gravitational effects on galaxies and galaxy clusters. Dark matter makes up about 85% of all matter in the universe. Some researchers suggested that dark matter might clump differently than normal matter, creating larger structures faster. Simulations testing this idea still cap out at the 1.2 billion light-year limit. Dark matter helps, but does not solve the problem. A more radical idea questions whether gravity works the same way at cosmic scales as it does in our local region of space. Maybe the force of gravity gets slightly stronger over distances of billions of light years. This would allow structures to form faster and grow larger than standard physics predicts. The challenge is that changing how gravity works has enormous consequences for all of cosmology. You cannot tweak one thing without affecting everything else. Some scientists went back to the data itself. They argued that the Great Wall might be a projection effect. Imagine looking at stars in the night sky. They appear to form patterns like constellations, but those patterns are illusions. The stars are at vastly different distances. They only look connected from our viewpoint. Maybe the gamma-ray bursts are doing the same thing, creating the illusion of a structure when they are actually scattered at different distances. This argument fell apart under scrutiny. The redshift measurements confirmed all the bursts occurred at approximately the same distance. They were not at different depths, creating a false pattern. They genuinely clustered together in three-dimensional space. Every conventional explanation failed. The Great Wall violated the theoretical size limit because the theoretical limit assumed our models were complete. Apparently, they are not. Gravity is the weakest of the four fundamental forces in physics. Electromagnetic force is about 1 billion billion times stronger than gravity at atomic scales. Yet gravity dominates cosmic structure. It holds planets in orbit. It binds stars into galaxies. It pulls galaxies into clusters. At large scales, gravity is the only force that matters. This happens because gravity is always attractive and has infinite range. Electromagnetic force can push or pull, so opposite charges cancel out at large distances. Strong and weak nuclear forces only work at subatomic scales. Gravity affects all matter equally and never turns off. Over cosmic distances and timescales, gravity always wins. The strength of gravitational attraction depends on mass and distance. Double the mass and you double the pull. Double the distance and the pull drops to 1/4 strength. This inverse square relationship means gravity gets weaker rapidly as objects move apart. At cosmic scales, even though galaxies contain enormous mass, they sit so far apart that the gravitational force between them is incredibly weak. This weakness limits how fast structures can grow. When matter is spread thin across space, gravitational attraction between different regions is subtle. It takes billions of years for that gentle pull to draw enough matter together to form something like a galaxy cluster. Building something bigger requires even more time because the forces are even weaker across those larger distances. Computer simulations model this process by starting with the conditions of the early universe and letting gravity do its work. Researchers input the known amounts of normal matter and dark matter, apply the laws of gravity, and fast forward through cosmic history. These simulations recreate the universe we see remarkably well. They produce galaxies, clusters, superclusters, and voids that match observations. Except they never produce anything like the Great Wall. No matter how researchers adjust the initial conditions within observed limits, no matter what variations they introduce, the simulations consistently create structures that max out around 1.2 billion light-years. They have run thousands of simulations using different parameters. The results remain the same. Some researchers tried artificially boosting the strength of gravity in their simulations to see if stronger gravitational forces could produce larger structures faster. The answer is yes. If you make gravity about 3 times stronger than it actually is, you can get structures approaching the size of the Great Wall to form in the available time. But we know gravity is not 3 times stronger than we measure it to be. We have tested gravitational strength extensively at many different scales. The measurements are precise and consistent. This creates a logical problem. Gravity, as we measure it, cannot produce the Great Wall in the time available. Yet the Great Wall exists. Therefore, either our measurements are wrong, our understanding of how gravity operates at cosmic scales is incomplete, or something else besides gravity contributed to forming this structure. None of these options are comforting. The first suggests our entire framework of physics is off. The second requires rewriting general relativity. The third implies forces or effects we have not discovered yet, and there is still more that does not add up. The universe began 13.8 billion years ago with the Big Bang. We know this age precisely from multiple independent measurements. The cosmic microwave background radiation gives us one number. The expansion rate of the universe gives us another. The ages of the oldest stars give us a third. All these methods converge on the same age. The uncertainty is less than 1%. This timeline creates strict limits on what can exist. Nothing in the universe can be older than 13.8 billion years. Nothing can have formed before the conditions allowed stable matter to exist. Nothing can be larger than gravity could build in the time available. These are not theoretical constraints. They are observational facts based on physics we can measure and test. The Great Wall appears in our observations at a redshift, indicating we see it as it existed 10 billion years ago. That means it formed sometime in the first 3.8 billion years after the Big Bang. Remember, structure formation could not begin immediately. The early universe was too hot. Atoms could not form until about 380,000 years after the Big Bang. The first stars took 200 million years to appear. Galaxies needed several hundred million more years to assemble. Being generous, stable structure formation began around 500 million years after the Big Bang. That leaves approximately 3.3 billion years for the Great Wall to form before we observe it in our data. 3.3 billion years for gravity to pull together matter across 10 billion light-years of space and organize it into a coherent structure. Here is why that timeline is impossible. Even light traveling at its maximum speed of 670 million miles per hour can only cross 3.3 billion light-years in 3.3 billion years. That is the absolute fastest that any force or influence can propagate through space according to relativity. Gravity moves at the same speed as light. This means regions of the Great Wall, separated by more than 3.3 billion light-years, could not have influenced each other at all during the formation period. Think of it like trying to coordinate a construction project where your work crews cannot communicate with each other. They are too far apart for signals to reach between them in the time available. Yet somehow they all build parts of the same structure that perfectly connect. Either they coordinated before your time limit began, which is impossible because nothing existed then, or they are following some blueprint we cannot see. The standard model of cosmology has no mechanism for creating coordinated structures across distances where coordination should be impossible. Inflation solved a similar problem in the very early universe by suggesting distant regions were once close together before rapid expansion separated them. But inflation ended a tiny fraction of a second after the Big Bang. It cannot explain coordination on the time and distance scales of the Great Wall formation. Some scientists suggested we might be seeing multiple unrelated structures that happen to line up from our perspective. The statistical analysis rules this out. The probability of multiple structures randomly aligning this way is negligible. The timeline problem has no conventional solution. The Hercules Corona Borealis Great Wall was shocking, but it was not the first time astronomers found cosmic structures that challenged our size expectations. The history of discovering larger and larger formations shows a pattern. Each time we improve our ability to map the universe, we find something bigger than theory predicted. In 1989, astronomers Margaret Geller and John Huckra discovered what they called the Great Wall. This structure stretched about 500 million light-years across space, making it the largest known structure at that time. It consisted of superclusters and galaxy filaments arranged in a sheet-like formation. The discovery prompted questions about how something that large could form, but it still fell within theoretical limits. Scientists adjusted their models and moved on. Then in 2003, a team analyzing the Sloan Digital Sky Survey found something bigger. The Sloan Great Wall measured approximately 1.4 billion light-years across. This structure pushed right up against the theoretical maximum size limit. Some cosmologists began questioning whether that limit was real or just a guideline. The structure was enormous, but not quite impossible. It sat at the edge of what physics allowed. 2004 brought another surprise. Researchers identified a massive cosmic void called the Eridanus supervoid. This was not a structure made of matter, but rather a region with significantly less matter than surrounding areas. It spanned about 1 billion light-years. Large voids raise different questions than large structures, but they still challenge the cosmological principle. The universe should not have such dramatic variations in density at these scales. In 2007, astronomers found a grouping of quasars spanning 4 billion light-years. Quasars are actively feeding black holes in the centers of distant galaxies. Finding them clustered together was unexpected. Finding them clustered across 4 billion light-years was startling. This structure exceeded the theoretical limit by more than 3 times. However, some scientists argued it might be a chance alignment rather than a gravitationally bound structure. The debate continued. Then, in 2013, came the Hercules Corona Borealis Great Wall. At 10 billion light-years, it dwarfed everything found before. It was not sitting at the edge of theoretical limits. It was not questionably beyond them. It was definitively, undeniably, impossibly large by factors that could not be explained away by measurement error or statistical fluctuation. This progression suggests a troubling possibility. Maybe the theoretical size limit is not a real limit at all. Maybe it is just the point where our models break down because they are incomplete. Each new generation of telescopes and surveys reveals larger structures. Each discovery pushes further, beyond what we thought possible. The pattern implies we might not have seen the largest structures yet. We are limited by how far into space we can observe and how much sky we can survey in detail. There could be even larger formations waiting to be discovered in regions we have not mapped thoroughly, or farther away than our current instruments can detect clearly. If the Great Wall is not unique, if structures this size are common, then our entire understanding of how the universe organizes itself needs revision. The Sloan Great Wall held the record for largest cosmic structure for 10 years. Discovered using data from the Sloan Digital Sky Survey, it measured 1.4 billion light-years long. This placed it right at the theoretical maximum size that gravity should be able to produce in the time available since the Big Bang. Astronomers thought this might be the natural limit, the biggest thing the universe could build. The Sloan Great Wall sits about 1 billion light-years from Earth. We can see it more clearly than the Hercules Corona Borealis Great Wall because it is closer and contains more luminous galaxies. Detailed surveys mapped its shape and structure. It appears as a massive sheet of galaxy clusters separated by voids, creating a foam-like pattern across space. Imagine bubble wrap at cosmic scale, with each bubble made of galaxy clusters. What made the Sloan Great Wall acceptable to cosmologists was its size. At 1.4 billion light-years, it pushed against theoretical limits but did not break them. Researchers could explain its formation using known physics and slightly generous assumptions about early density fluctuations. The structure required everything to go right gravitationally, but it was possible, barely possible, but possible. After its discovery, cosmologists revised their expectations. They assumed 1.4 billion light-years represented the practical upper limit for cosmic structures. Anything larger would require physics we had not observed. Theoretical limits exist for a reason. They define the boundaries of what natural processes can achieve. Finding something at that boundary makes sense. Finding something far beyond it means your understanding is wrong. The Sloan Great Wall also confirmed that the universe organizes matter into a cosmic web. This web consists of filaments and sheets of galaxies surrounding enormous voids where few galaxies exist. The structure looks like a three-dimensional spiderweb, stretching across the universe. Gravity pulls matter into the densest filaments, leaving voids behind. This web structure appears throughout the observable universe at distances where we can map galaxy positions clearly. Computer simulations reproduce this cosmic web structure accurately when you input the right amounts of matter, and dark energy. The simulations show how tiny variations in the early universe grow into filaments and voids over billions of years. They match observations well. They predict the size and spacing of structures we actually see. They give cosmologists confidence that the underlying physics is correct. Those same simulations consistently fail to produce structures larger than about 1.2 billion light-years. Even when researchers adjust parameters within reasonable ranges, the simulations create cosmic webs with filaments and sheets that max out near the Sloan Great Wall size. This is why astronomers thought 1.4 billion light-years was the ceiling. Theory and observation agreed. Then the Hercules Corona Borealis Great Wall appeared in the data. At 10 billion light-years, it was 7 times larger than the Sloan Great Wall. It was not slightly beyond theoretical limits. It was absurdly beyond them. If the Sloan Great Wall represented everything going perfectly right for structure formation, the Hercules Corona Borealis Great Wall represented something fundamentally different, something that operates by rules we have not discovered. Dark matter changed everything in cosmology. We cannot see it directly. We cannot detect it with telescopes. We know it exists because galaxies rotate too fast to be held together by the gravity of visible matter alone. Stars at the edges of galaxies orbit at speeds that should fling them into space. They stay in orbit because invisible mass creates extra gravitational pull. That invisible mass is dark matter. Dark matter outweighs normal matter by about 5 to 1. For every atom of normal matter in the universe, there are 5 units of dark matter. This means most of the gravitational force shaping cosmic structure comes from matter we cannot see. Dark matter creates the scaffolding. Normal matter follows that scaffolding, lighting up the structure so we can observe it. Computer simulations show how this works. Start with the early universe filled with both types of matter distributed almost uniformly. Let gravity amplify small variations in density. Dark matter clumps together first because it only interacts through gravity. It ignores electromagnetic forces that would slow down normal matter. These dark matter clumps then pull normal matter toward them. Gas falls into the clumps, heats up, and eventually forms stars and galaxies. The result is a cosmic web where dark matter filaments connect galaxy clusters. The filaments act like highways. Galaxies move along them, merging and growing. The densest intersections in the web become massive galaxy clusters containing thousands of galaxies. Voids form in between where little matter exists. This picture explains the structure we observe throughout the universe. It also explains why structures have a size limit. Dark matter starts clumping early, but it still needs time to pull matter together across large distances. The clumps grow by consuming nearby matter and merging with other clumps. This process has a maximum speed determined by how fast matter can move and how much time has passed since the Big Bang. Even with dark matter helping, there is only so much structure you can build in 13.8 billion years. Simulations that include dark matter create realistic cosmic webs with structures up to about 1.2 billion light-years across. These simulations accurately reproduce the galaxy clusters, filaments, and voids we observe. The match between simulation and observation gives cosmologists confidence they understand large-scale structure formation. Dark matter is the key ingredient that makes it all work. Yet, those same simulations cannot produce the Hercules Corona Borealis Great Wall. Researchers tried boosting the amount of dark matter. They tried making it clump faster. They tried giving it different properties within limits consistent with other observations. None of these modifications created structures approaching 10 billion light-years. The simulations stubbornly refused to build anything that large in the time available. This suggests dark matter scaffolding has limits just like normal gravity. You can only pull matter together so fast even when most of it is dark. The Great Wall exceeds those limits by such a wide margin that adjusting dark matter properties within reasonable ranges makes no difference. Something else must be involved. Or everything we think we know about how structure forms is missing a critical component. Not all astronomers agree the Hercules Corona Borealis Great Wall is real. Some argue it represents a statistical coincidence rather than a physical structure. They point out that if you look at enough random data, patterns will emerge by pure chance. Deal enough card hands, and eventually you will get a royal flush. Map enough gamma-ray bursts, and eventually some of them will line up. This argument relies on probability. The universe contains billions of gamma-ray bursts. We have only detected and mapped thousands of them. If the observed clustering represents a tiny fraction of random bursts that happen to align, then there is no structure. Just a pattern that looks meaningful but actually tells us nothing about how matter is distributed in space. The Discovery team addressed this criticism directly. They calculated the statistical significance of the clustering. Their analysis showed the probability of this pattern occurring randomly at less than 1 in 2,000. That is far below the threshold scientists typically use to confirm a discovery. In particle physics, researchers require odds of about 1 in 3.5 million before declaring a new particle discovered. But in astronomy, 1 in 2,000 is considered strong evidence. Other researchers repeated the statistical analysis using different methods. Some found slightly different probability values, but all confirmed the clustering was statistically significant. The gamma-ray bursts were concentrating in this region far more than random chance would explain. This concentration indicated something physical occupied that space. The strongest evidence comes from cross-referencing. The gamma-ray bursts are not the only indication of structure in that region. Optical surveys that map galaxy positions show enhanced galaxy density along the same line of sight. Radio observations detect more activity in that area. X-ray data from galaxy clusters align with the burst positions. Multiple independent datasets point to the same conclusion. Matter concentrates there. Critics also questioned whether the structure is gravitationally bound. A true cosmic structure should be held together by gravity. The galaxies and clusters should be influencing each other gravitationally, moving together as a unit. Some researchers argued the Great Wall might be a projection effect, where unrelated structures at different distances appear connected from our viewpoint. This criticism is harder to dismiss completely. Measuring precise distances to individual galaxies in the Great Wall is difficult because they are so far away. The redshift measurements tell us approximate distances, but there is always some uncertainty. It is possible some of the galaxies are closer or farther than they appear, creating the illusion of a connected structure. However, the consistency of redshift values across the entire structure suggests otherwise. If this were random alignments of unrelated objects, we would expect to see more scatter in their distances. Instead, the measurements cluster tightly around the same redshift range. This indicates the galaxies genuinely occupy the same region of space, rather than being spread across different distances. The debate continues in astronomy literature. Some scientists remain unconvinced. They want more data, better measurements, additional confirmation before accepting a structure this large. But the weight of evidence increasingly supports that the Great Wall is real, and possibly not alone. Mapping the universe requires looking at it in 3 dimensions. When astronomers photograph the sky, they capture a 2-dimensional image showing where objects appear on the celestial sphere. This tells you the direction to a galaxy, but nothing about its distance. To build a 3-dimensional map, you need to measure how far away each galaxy sits. Distance measurements in astronomy rely primarily on redshift. When light travels through expanding space, its wavelength stretches. This stretching shifts the light toward the red end of the spectrum. The farther light travels, the more space expands during its journey, and the more the wavelength shifts. By measuring how much a galaxy's light has shifted, astronomers calculate its distance. This technique works because the universe is expanding uniformly. Galaxies farther away move away from us faster than nearby galaxies. The relationship between distance and speed is predictable and well tested. Measure the speed a galaxy recedes by measuring its redshift, and you can calculate its distance. This is how astronomers map large-scale cosmic structure. The gamma-ray bursts that revealed the Great Wall all showed redshifts between 1.6 and 2.1. These values translate to a distance of roughly 9 to 10 billion light-years. More importantly, they indicate all the bursts occurred at approximately the same distance from Earth. They were not scattered throughout space at different depths. They clustered together in three-dimensional space, not just in our line of sight. Three-dimensional mapping reveals the cosmic web. When you plot millions of galaxies by their positions and distances, a pattern emerges. Galaxies concentrate along filaments that connect at massive clusters. Between the filaments sit voids containing few galaxies. The structure looks organic, almost biological, like neural networks in a brain or blood vessels in tissue. This web exists because matter follows the path of least resistance. Dense filaments form where gravity is strongest. Matter flows along these filaments toward the densest intersections. Voids form where initial matter density was below average. Once matter starts leaving a region, gravity accelerates the process. The void empties out as surrounding matter drains into adjacent filaments. The Hercules Corona Borealis Great Wall appears as an unusually long and massive filament in this cosmic web. Instead of stretching a few hundred million light-years like typical filaments, it extends for 10 billion light-years. Instead of containing a few galaxy clusters, it contains thousands. It is not a different type of structure. It is the same type of structure scaled up beyond what should be possible. Three-dimensional mapping also reveals something unsettling. The Great Wall is not aligned randomly in space. It has a specific orientation relative to other large-scale structures in the observable universe. Some researchers noticed that several of the largest cosmic structures seem to align with each other, creating what looks like an axis through the observable universe. This alignment should not exist if the universe is truly uniform and isotropic as the cosmological principle requires. The more we map the universe in 3 dimensions, the more we find patterns that challenge our assumption of cosmic uniformity. Patterns that suggest the universe has structure even on the largest scales we can observe. Cosmic filaments connect galaxy clusters like bridges connecting cities. These structures form naturally as gravity pulls matter along paths of maximum density. Early in the universe, matter was distributed almost uniformly, but tiny variations existed. Gravity amplified these variations over billions of years. Denser regions attracted more matter. Less dense regions lost matter to their surroundings. The result is a network where matter concentrates along lines, linking the densest points. Think of water flowing across uneven ground. It follows paths determined by the landscape, concentrating in channels that become streams and rivers. Cosmic filaments work similarly. Matter follows gravitational channels, creating dense streams of galaxies flowing between massive clusters. These filaments contain gas, dark matter, and galaxies. The gas inside filaments can reach temperatures of millions of degrees due to gravitational heating. When matter falls into a filament, it accelerates and collides with other matter already there. These collisions convert gravitational potential energy into heat. The heated gas glows in X-rays, allowing telescopes to map the filaments directly, even though most visible galaxies may be sparse. Measurements show typical filaments measure about 300 to 500 million light-years long and 10 to 50 million light-years wide. They connect galaxy clusters that contain hundreds to thousands of galaxies each. The matter within a filament is not stationary. Galaxies move along the filament toward the densest clusters at speeds of hundreds of miles per second. This movement represents matter continuing to organize itself into increasingly concentrated structures. The Hercules Corona Borealis Great Wall dwarfs these typical filaments. If standard filaments are rivers, the Great Wall is an ocean current stretching across an entire planet. The scale difference is not just quantitative, it raises qualitative questions about how such a structure could form through the same gravitational processes that create normal filaments. Standard filaments form when matter collapses along one dimension while still expanding in the other two. Imagine a cloud of gas that starts pulling together. If it pulls together equally in all directions, it forms a sphere like a planet or star. If it pulls together along one axis faster than the others, it forms a filament. Computer simulations show this happens naturally when you start with the slight density variations observed in the early universe. But those simulations predict filaments should rarely exceed 500 million light-years in length. The Great Wall is 20 times longer. For it to form as a single filament, the initial density variation in the early universe would need to be 20 times larger and 20 times more extended than any variation we observe in the cosmic microwave background radiation. Those large variations would show up clearly in the temperature fluctuations of the background radiation. They are not there. Another possibility is that the Great Wall is not a single filament, but many shorter filaments aligned coincidentally. Statistical analysis makes this unlikely. The probability of multiple independent filaments lining up across 10 billion light-years is extremely small. Even if it happened, we would expect to see gaps between the segments. The gamma-ray burst data shows continuous clustering along the entire length. Cosmic filaments explain the smaller structures we observe throughout the universe. They fail to explain the Great Wall. The cosmological principle states that the universe is homogeneous and isotropic. Homogeneous means it has the same properties everywhere. Isotropic means it looks the same in all directions. These assumptions form the foundation of modern cosmology. Without them, Einstein's equations describing cosmic expansion have no unique solution. You cannot build a coherent model of the universe. This principle emerged from early 20th century observations. Astronomers noticed galaxies spreading uniformly across the sky. Later surveys confirmed this uniformity extended in all directions. Statistical analyses showed no preferred orientation or concentration. The universe appeared the same whether you looked toward Hercules, Orion, or any other constellation. This uniformity supported the idea that Earth occupies no special location in the cosmos. The cosmological principle allows for small-scale variations. Galaxies cluster. Clusters group into superclusters. Voids exist between structures, but these variations should average out when you examine large enough regions of space. By the time you look at scales of hundreds of millions of light-years, the universe should appear smooth and uniform. Any given volume of space that large should contain roughly the same amount of matter as any other volume. The Hercules Corona Borealis Great Wall challenges this uniformity directly. It creates a massive concentration of matter along one direction in space. If you examine a volume 10 billion light-years long in the direction of the Great Wall, it contains far more matter than a volume of the same size in a perpendicular direction. The universe is not uniform at that scale. It has preferred directions and preferred locations. Some physicists argue this does not necessarily break the cosmological principle. They suggest the Great Wall might be a local anomaly. If the observable universe is large enough and you allow for statistical variations, occasionally you should see unusually large structures. These would be rare, but rare things happen sometimes. The universe could still be uniform on average, even if individual regions show extreme variations. This argument weakens when you consider the other large structures discovered in recent years. The Sloan Great Wall, the quasar clustering, the massive cosmic voids. Each discovery adds another example of the universe showing structure at scales where it should be uniform. If these are all rare statistical flukes, we are incredibly unlucky to be observing during a time when multiple flukes appear in our surveys. More troubling is the alignment problem. Several large-scale structures appear oriented along similar axes. They are not randomly distributed in all directions. They show preferred orientations. This suggests the universe might have large-scale structure even beyond what we can map directly. It hints at organization on scales approaching the size of the observable universe itself. If the cosmological principle is wrong, then many of our conclusions about the universe need revision. Dark energy estimates depend on assuming uniform expansion. The age of the universe derives from models assuming homogeneity. The Big Bang theory itself relies on the principle for most of its predictions. Questioning the principle means questioning the entire framework of modern cosmology. Yet the Great Wall sits in our data, confirmed by multiple observations, measured repeatedly. Real in every sense that matters scientifically. It exists, whether our principles allow it to or not. Redshift measurements confirm the Hercules Corona Borealis Great Wall exists at a specific distance, not scattered across space at different depths. When astronomers measure the redshift of galaxies or gamma-ray burst host galaxies along the Great Wall, they consistently get values between 1.6 and 2.1. This tight clustering of redshift values proves the structure occupies a defined region of three-dimensional space. Redshift works because the universe is expanding. As space expands, it stretches the wavelength of light traveling through it. Light that started out blue shifts toward red. Light that started out red shifts into infrared. The amount of shifting depends on how much the universe has expanded during the light's journey. Light from farther away travels longer and gets stretched more. Measure the stretch and you know the distance. The relationship between redshift and distance is not simple. You cannot just multiply redshift by the speed of light to get distance. The universe's expansion rate has changed over time. It was faster in the past when matter was denser. It accelerated in more recent epochs due to dark energy. Calculating distance from redshift requires accounting for this changing expansion rate, using the full framework of cosmology. For the Great Wall, redshift values between 1.6 and 2.1 translate to distances around 9 to 10 billion light-years. These measurements use the standard cosmological model that includes matter, dark matter, and dark energy, in proportions confirmed by multiple independent observations. The uncertainty in the distance is relatively small, perhaps plus or minus a few 100 million light-years. That uncertainty does not affect the conclusion. The Great Wall is real and impossibly large. What makes redshift especially powerful is its precision. Modern spectrographs can measure redshift to accuracy better than 1 part in 10,000. This allows astronomers to determine not just that galaxies are far away, but exactly how far away they are relative to each other. Galaxies clustered in space will show similar redshifts. Galaxies spread across different distances will show a broad range of redshifts. The gamma-ray bursts defining the Great Wall show remarkably consistent redshifts. If these bursts were randomly scattered through space at different distances but happened to align from our perspective, we would expect to see significant variation in their redshifts. Instead, they cluster tightly around the same values. This consistency proves they occupy the same cosmic neighborhood despite being separated by billions of light-years across the sky. Some researchers attempted to explain away the Great Wall by suggesting systematic errors in redshift measurements. Maybe something about gamma-ray bursts or their host galaxies causes redshift to be measured incorrectly. Maybe dust between us and the bursts absorbs light in ways that mimic redshift. These proposals were tested and found lacking. Independent redshift measurements using different methods confirmed the original values. The consistency across multiple datasets rules out systematic errors. The precision of redshift measurements leaves no room for the Great Wall to be an illusion or measurement artifact. It exists where the data says it exists. At the distance, the data indicates. With the impossible size that follows from combining position and distance measurements, physics must explain it, even if current physics cannot. When confronted with something that breaks your models, you have 3 options: deny the observation, modify the models, or create entirely new physics. The astronomy community exhausted the first option. Multiple independent datasets confirm the Great Wall exists. That leaves modifying existing theories or proposing radical new ideas. One competing theory suggests modified Newtonian dynamics might explain large-scale structures better than general relativity. This idea, called MOND, proposes that gravity behaves differently at extremely low accelerations. In galaxy clusters and cosmic filaments, gravitational acceleration is incredibly weak. MOND predicts gravity becomes slightly stronger under these conditions than Einstein's equations suggest. Stronger gravity at cosmic scales would allow structures to form faster and grow larger. The Great Wall might be possible if gravity has a boost we have not accounted for. The problem is, MOND was designed to explain galaxy rotation curves, not cosmic megastructures. When researchers apply MOND to structure formation simulations, they get results that conflict with observations of the cosmic microwave background radiation. MOND solves one problem while creating several others. Another approach involves quantum gravity effects. Standard cosmology treats space as smooth and continuous. Quantum mechanics suggests space might have a granular structure at the smallest scales. Some physicists propose these quantum properties could influence structure formation in ways we have not calculated. Tiny quantum effects operating over billions of years might amplify into large-scale structures beyond classical predictions. This theory remains highly speculative. We have no experimental evidence for quantum gravity effects at cosmic scales. The mathematics is incomplete. The predictions are vague. It offers an interesting possibility, but no concrete mechanism for producing the Great Wall. A third proposal looks at the role of primordial magnetic fields. The early universe might have contained magnetic fields threading through space. These fields could have influenced how matter clumped together, creating preferred directions for structure formation. Magnetic fields can accelerate structure growth by channeling matter along field lines, potentially producing longer filaments than gravity alone would create. Computer simulations testing this idea show magnetic fields can enhance structure size by perhaps 50%. That helps, but does not bridge the gap between the theoretical maximum and the observed size of the Great Wall. You would need magnetic fields thousands of times stronger than any evidence suggests existed in the early universe. Some cosmologists propose the structure might have formed earlier than we think, before the epoch when standard structure formation began. If density variations existed in the universe before inflation, they might have been stretched to enormous scales during the inflationary period. These supersized variations could seed structures larger than normal quantum fluctuations allow. The challenge here is that inflation should erase any pre-existing structures. The exponential expansion smooths out variations, leaving only quantum fluctuations as seeds for later structure formation. Getting around this requires special conditions during inflation that have no observational support. Each competing theory attempts to explain the Great Wall by modifying one aspect of standard cosmology. None of them work completely. They either predict other effects we do not observe or require fine-tuning that seems implausible. The Great Wall resists explanation by simple modifications to existing physics. It demands something more fundamental. Between the galaxy clusters and filaments lie the cosmic voids. These regions contain very few galaxies compared to the universe's average density. Some voids span hundreds of millions of light-years across. Inside them, you might find only a handful of small galaxies scattered through space that could contain thousands. The voids are not completely empty, but they are far emptier than theory predicts. Matter leaves voids for a simple reason. Gravity pulls it toward denser regions. Imagine a region of space that starts with slightly below average matter density. Nearby regions with average or above average density exert stronger gravitational pull. Matter at the edge of the low-density region feels this pull and starts drifting toward denser areas. As matter leaves, the void becomes even less dense. The process accelerates. Over billions of years, voids empty out, while filaments grow denser. But matter does not leave instantly. The process takes time. Galaxies in voids still exist because they formed before the void emptied completely. These void galaxies provide clues about cosmic evolution. They evolved in isolation, experiencing fewer galaxy mergers than their counterparts in dense regions. Studying them shows us what happens when galaxies develop without constant gravitational harassment from neighbors. The space inside voids is not truly empty. It contains dark matter, diffuse gas, and dark energy. The dark matter forms tenuous filaments even within voids, though much less dense than the major cosmic filaments. Gas inside voids remains extremely thin, often just a few atoms per cubic meter. This gas is difficult to detect, but plays a role in the overall matter budget of the universe. Dark energy dominates inside voids. In dense regions, matter and dark matter exert significant gravitational influence, despite dark energy being present. Inside voids, with matter spread so thin, dark energy's repulsive effect faces little opposition. This causes voids to expand faster than the universe's average expansion rate. They grow larger over time, pushing surrounding matter into denser filaments. The Great Wall creates enormous voids on either side of its structure. If the Great Wall is 10 billion light-years long and contains concentrated matter, then adjacent regions must have below-average density to maintain the universe's overall average density. These voids might be equally massive, equally anomalous, but far harder to detect because empty space reveals itself only by the absence of light. Mapping these voids requires surveying huge volumes of space and noting where galaxies should be but are not. This is like trying to map holes in Swiss cheese by counting the cheese. You need complete surveys covering large areas. The voids adjacent to the Great Wall sit at distances where our surveys become incomplete. We see hints of vast empty regions but cannot map them precisely. What happens to matter over billions of years in such voids? It becomes increasingly isolated. Void galaxies burn through their gas, form their stars, and eventually go quiet. No new gas falls in to fuel fresh star formation. The galaxies fade to red as their bright blue stars age and die. Eventually, these galaxies become nearly invisible, containing only old red stars and stellar remnants. The voids grow, the filaments concentrate, and structures like the Great Wall become more extreme over time. The cosmic microwave background radiation is the oldest light in the universe. It comes from 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This radiation fills all of space, coming from every direction at once. It provides a snapshot of the universe in its infancy. Telescopes measuring this background radiation find it remarkably uniform. The temperature is 2.7 degrees above absolute zero in every direction. Variations in temperature across the sky amount to only about 1 part in 100,000. This uniformity confirms the cosmological principle. The early universe was incredibly smooth, but those tiny variations matter enormously. They represent the seeds of all structure we see today. Slightly warmer spots indicate regions with slightly higher matter density. Slightly cooler spots indicate lower density. Gravity amplified these variations over billions of years. Dense regions became galaxy clusters. Low-density regions became voids. The temperature map of the cosmic microwave background is a baby picture of the cosmic web. Scientists have mapped these temperature variations with extreme precision. Satellites like WMAP and Planck measured the fluctuations to accuracy better than 1 part in a million. These measurements show that initial density variations were tiny, too tiny to produce structures as large as the Hercules Corona Borealis Great Wall through normal gravitational growth. The size of variations in the cosmic microwave background correlates directly with the size of structures that can form. Larger initial variations produce larger final structures. The maximum variation size we observe in the background radiation predicts structures should not exceed about 1.2 billion light-years. This prediction matches computer simulations perfectly. It matches most observations of cosmic structure well, except it fails to predict the Great Wall by a factor of 8. Some researchers searched for anomalies in the cosmic microwave background that might explain unusually large structures. They looked for regions with stronger than average variations. They analyzed the pattern for unexpected features. They found a few interesting anomalies, including something called the cold spot, an unusually large, cool region that might indicate a supervoid. But nothing in the background radiation predicts a structure as large as the Great Wall. The absence of corresponding features in the cosmic microwave background creates a serious problem. If the Great Wall formed from initial density variations, those variations should leave clear signatures in the background radiation. We should see an elongated region of slightly higher temperature stretching across 10 billion light-years of the early universe. We do not see this. The background radiation shows no indication that seeds for such a massive structure existed. This suggests two possibilities. Either the Great Wall did not form from initial density variations, which contradicts our entire understanding of structure formation, or something happened between the cosmic microwave background era and the present that created structures from processes we do not understand. A third possibility is even more disturbing. Maybe the features are there in the cosmic microwave background, but we have not recognized them. Perhaps they appear in patterns we dismissed as noise or statistical fluctuations. If so, we have been looking at evidence of the Great Wall since we first mapped the background radiation. We just did not know what we were seeing. Computer simulations of cosmic structure formation are remarkably successful. Start with the conditions of the early universe as measured from the cosmic microwave background. Add the known amounts of normal matter, dark matter, and dark energy. Apply the laws of gravity. Let the simulation evolve forward through 13.8 billion years of cosmic history. The result matches reality. The simulations produce galaxies, galaxy clusters, filaments, and voids. The sizes and spacing of these structures align with observations. The timeline of galaxy formation matches what we see when we look at distant, ancient galaxies. The simulations reproduce the cosmic web in stunning detail. This success gives cosmologists confidence they understand the fundamental processes shaping the universe. Thousands of these simulations have been run on supercomputers worldwide. Researchers vary the parameters to test different scenarios. They adjust the amount of dark matter. They modify the strength of initial density fluctuations. They try different models for dark energy. They change the cosmological constant. Every variation produces similar results. Structures form and grow, but they cap out at approximately 1.2 billion light-years. No simulation has ever produced anything resembling the Hercules Corona Borealis Great Wall. Researchers specifically tried to recreate it by optimizing every parameter for maximum structure size. They started simulations with the largest allowable initial variations. They boosted dark matter density. They minimized dark energy's effect. Even under these ideal conditions, the simulations created structures only about 1.5 billion light-years across. The failure is not subtle. The simulations missed the target by a factor of 6 to 7. This is not a small discrepancy you can explain by measurement uncertainty or computational limits. The simulations definitively predict that structures the size of the Great Wall cannot exist. Yet observations definitively show they do exist. Some researchers questioned whether the simulations might be missing important physics. Maybe gravitational calculations break down at cosmic scales in ways we have not noticed. Maybe dark matter has properties that only become important in the largest structures. Maybe there are feedback effects between normal matter and dark matter we have not included. Teams added more complexity to their simulations. They included magnetic fields. They modeled gas dynamics in greater detail. They incorporated the effects of black holes and stellar feedback. They tried alternative theories of gravity. None of these additions changed the outcome significantly. The maximum structure size remained around 1.2 billion light-years. The computational power behind these simulations is staggering. Modern cosmological simulations track billions of particles representing matter throughout the universe. They calculate gravitational forces between all these particles over billions of years of evolution. This requires some of the world's most powerful supercomputers running for weeks. The simulations capture physics at scales from individual galaxies up to the entire observable universe. Yet they fail to produce one specific structure we observe. This failure is more than an embarrassment. It represents a fundamental gap in our understanding. The simulations work everywhere else. They match countless observations. They predict the universe we see, except for this one glaring exception. Something creates the Great Wall through processes our best physics cannot simulate, something we have not discovered yet. Gravity is the most thoroughly tested force in physics at small and medium scales. We know how it works between planets. We understand it for binary stars. We can predict the orbits of spacecraft with incredible precision. General relativity describes gravity near black holes and neutron stars with perfect accuracy, but cosmic scales are different. The distances are billions of light-years. The masses are trillions of times larger than anything we can test directly. What if gravity behaves slightly differently at these extremes? Small modifications to gravitational strength at cosmic scales could allow larger structures to form without affecting smaller systems, where we have tested gravity thoroughly. This idea attracts physicists because it offers a potential solution to the Great Wall problem without overturning everything we know. One proposal suggests gravity might have a very small positive feedback effect at large distances. Normally, gravity weakens with distance following the inverse square law. Double the distance, and gravity drops to 1/4 strength. This relationship has been tested extensively. But what if, at distances beyond 1 billion light-years, gravity stops weakening quite so fast? A tiny deviation from inverse square, perhaps 1 part in 10,000, would be undetectable in normal tests, but could accumulate at cosmic scales. Stronger gravity at extreme distances would allow structures to pull together faster. The Great Wall might have formed in the available time if gravity provided just a small boost over billions of light-years. Calculations show you need gravity to be only about 2% stronger at cosmic scales to make the Great Wall possible. That is a small enough modification that it might hide within our measurement uncertainties. The problem is we have ways to test gravity at cosmic scales. Galaxy cluster dynamics show us how gravity behaves across millions of light-years. Gravitational lensing, where massive objects bend light from background galaxies, tests gravity across billions of light-years. The cosmic microwave background radiation constrains how gravity operated in the early universe. All these observations agree with standard general relativity. None of them show the 2% boost needed to explain the Great Wall. Another idea involves screening mechanisms. Perhaps gravity operates at full strength locally, but some effect screens or reduces it at the largest scales. This would allow local tests to give standard results while cosmic structure formation proceeds differently. Several theoretical frameworks propose mechanisms that could create this screening, usually involving additional scalar fields permeating space. These theories make predictions we can test. They affect how galaxy clusters behave. They influence the expansion rate of the universe. They change predictions for gravitational wave propagation. So far, observations have ruled out most screening mechanisms that would be strong enough to explain the Great Wall. The modifications required are either too large, affecting things we measure accurately, or too small, failing to solve the problem. A more radical possibility questions whether gravity alone governs cosmic structure. Maybe another force contributes at the largest scales. Perhaps dark energy does not just cause acceleration, but also has directional effects that enhance structure growth along certain axes. This would require dark energy to be more complex than current models assume. Testing these ideas requires pushing observations to their limits and comparing results against modified gravity predictions. So far, standard gravity keeps winning, except when it comes to the Great Wall. Dark energy makes up about 68% of everything in the universe. It drives the accelerating expansion of space itself. Unlike matter and gravity, which pull things together, dark energy pushes everything apart. This repulsive effect grows stronger as space expands because dark energy has constant density. More space means more dark energy means stronger repulsion. Scientists discovered dark energy in 1998 by measuring distant supernovae. These exploding stars appeared dimmer than expected, indicating the universe's expansion was accelerating. Something was pushing space apart faster than gravity could pull matter together. That something is dark energy, though we do not know what it actually is. We only know what it does. The standard model treats dark energy as the cosmological constant, a property of space itself that remains the same everywhere and always. Every cubic meter of space contains the same amount of dark energy, regardless of whether matter is present. This simplicity makes calculations tractable, but might be wrong. Dark energy could vary across space or change over time in ways we have not detected. The Hercules Corona Borealis Great Wall challenges this uniform picture. If dark energy truly has constant density everywhere, then its effects should not create structures. It should push all matter apart equally in all directions. Yet the Great Wall exists, suggesting matter behaved differently in that region of space compared to others. Either dark energy varied there, or something else overcame dark energy's repulsive effects. Some cosmologists propose dark energy might interact with matter in ways beyond simple repulsion. Perhaps dark energy couples to dark matter or normal matter through forces we have not identified. These interactions could affect how fast structures form. In most of the universe, dark energy works against structure formation by driving expansion. But in regions with specific conditions, the interactions might enhance structure growth instead of hindering it. This would require dark energy to have structure itself. Instead of being perfectly smooth, dark energy might have variations in density or strength across cosmic scales. Denser dark energy would push expansion faster, creating voids. Less dense dark energy would allow matter to clump more easily, creating filaments and walls. The Great Wall might mark a region where dark energy density dropped below average for billions of years. Testing this idea is difficult. Dark energy reveals itself through its effect on expansion, which we measure by observing how fast distant galaxies recede. These measurements average over huge volumes of space. Detecting variations in dark energy density across different regions requires extremely precise measurements of expansion rates in multiple directions. Current data is not quite good enough. Alternative models suggest dark energy is not constant over time. Maybe it was weaker in the early universe and grew stronger more recently. Weaker dark energy in the past would have allowed structures more time to grow before accelerating expansion kicked in. The Great Wall might have formed during an epoch when dark energy was negligible, then survived into the current era when dark energy dominates. Observations of the cosmic microwave background radiation and the distribution of galaxies constrain how much dark energy could have changed over time. The allowed variation is small, probably too small to explain the Great Wall. Something about dark energy does not fit the standard picture. The Great Wall points toward complexity we have not accounted for. The Hercules Corona Borealis Great Wall is not the only anomaly found at cosmic scales. As surveys map deeper into space and cover larger areas of sky, other unexpected features emerge. Each discovery adds weight to the idea that the universe at the largest scales does not behave as our models predict. In 2004, astronomers identified an enormous void called the Eridanus supervoid. This region spans about 1 billion light-years and contains significantly fewer galaxies than average. What makes it especially strange is its connection to the cold spot in the cosmic microwave background radiation. The cold spot is an unusually large, cool region that should not exist based on standard cosmological fluctuations. The supervoid might explain the cold spot through a process called the integrated Sachs-Wolf effect, but the void itself requires explanation. Another anomaly appeared in 2007 when researchers found a cluster of quasars stretching across 4 billion light-years. Quasars are supermassive black holes actively consuming matter in the centers of galaxies. Finding them grouped together was surprising. Finding them aligned across distances exceeding theoretical limits was shocking. Debate continues about whether this represents a true structure or a chance alignment, but the pattern is statistically significant. The Shapley supercluster presents a different kind of problem. This massive concentration of galaxy clusters sits about 650 million light-years from Earth. It contains mass equivalent to about 10,000 Milky Way galaxies and spans 300 million light-years. The supercluster exerts enough gravitational pull to affect the motion of our own local group of galaxies. We are being pulled towards Shapley at about 400 miles per second. The mass required to cause this motion exceeds what we can account for by counting visible galaxies and estimating dark matter. Researchers mapping galaxy distributions found what they call the axis of evil in the cosmic microwave background radiation. This is a pattern where the largest temperature fluctuations seem to align along a specific axis through space. The cosmological principle predicts no such alignment should exist. The universe should look the same in all directions. Yet multiple independent analyses confirm the pattern. Some scientists dismiss it as statistical noise. Others see it as evidence of fundamental asymmetry in the universe. The Great Attractor poses another mystery. This is a gravitational anomaly in intergalactic space toward which hundreds of thousands of galaxies appear to be flowing. It sits roughly 150 million light-years away in the direction of the Centaurus and Hydra constellations. Visible matter in that region cannot account for the gravitational pull. Dark matter must be involved, but the concentration required seems too large to form in the time available. Then there is the motion of galaxy clusters themselves. Large-scale surveys show clusters moving in unexpected ways. Instead of random motions in all directions, many clusters appear to flow together in the same direction. This motion pattern, called dark flow, suggests the clusters respond to gravitational influences from beyond the observable universe. If true, this means structure exists on scales larger than we can see. Each anomaly can be explained individually with enough creative theorizing, but taken together, they paint a picture of a universe more complex and structured at large scales than standard cosmology allows. The Great Wall is the most extreme example, but it is not alone. If the Hercules Corona Borealis Great Wall exists, logic suggests it might not be unique. The observable universe spans about 93 billion light-years across. We have mapped only a fraction of this volume in the detail needed to find structures like the Great Wall. Most of our deep surveys cover narrow slices of sky. Vast regions remain unexplored at the distances where the Great Wall sits. Discovering the Great Wall required 15 years of gamma-ray burst data covering a specific patch of sky. Obtaining similar data for the entire sky would take centuries at current detection rates. We may have found the Great Wall because we happened to survey the right region at the right depth. Other structures of similar size could exist in areas we have not examined thoroughly. This possibility disturbs cosmologists. One structure pushing theoretical limits might be a rare statistical fluctuation. Multiple structures would indicate something systematically wrong with our models. If the universe routinely produces formations 8 times larger than physics predicts, then our understanding of cosmic evolution is fundamentally incomplete. Some researchers calculated how many structures like the Great Wall might exist in the observable universe if they form through rare but possible statistical variations. The calculations suggest perhaps 2 to 5 such structures should exist throughout all of space. We have potentially found one. That leaves 1 to 4 others waiting to be discovered. If surveys eventually find multiple Great Walls, it confirms they represent extreme but natural outcomes of cosmic structure formation. But if we find more than 5, standard statistics breaks down. Too many extreme outliers suggests they are not outliers at all, but rather normal features we failed to predict. The theoretical framework would require major revision. Early searches in other regions of sky have found hints. There are concentrations of gamma-ray bursts in areas that might indicate similar structures at similar distances. None yet confirmed with the same statistical significance as the original Great Wall, but the patterns are suggestive. More data over more years will clarify whether these hints represent real structures or noise. The implications extend beyond cosmology. If structures this large are common, they affect estimates of the total matter content of the universe. They influence calculations of dark matter distribution. They change predictions for how galaxy formation proceeded over cosmic history. Multiple Great Walls would mean significant fractions of the universe's matter concentrate in these megastructures, leaving even larger voids between them. This would create a universe far more clumpy and irregular at the largest scales than current models assume. The cosmological principle would fail not just locally, but globally. The universe would have vast regions with very different properties depending on whether you sit inside a Great Wall structure or in the voids between them. For intelligent life, this matters. Galaxy formation rates differ between dense structures and voids. Star formation proceeds differently. The chemistry of planets forming from different stellar generations varies. If Great Walls are common, then the conditions suitable for life might concentrate in or around these structures. Or perhaps life thrives better in the calmer environments of voids. We do not know because we barely understand these structures exist. Finding multiple structures, like the Great Wall, would tell us our cosmic neighborhood is more chaotic and extreme than we ever imagined. The search continues across the sky. The cosmological principle relies on the idea that the universe has no preferred direction. Look north or south, east or west, up or down, and the universe should appear statistically the same. Galaxies might cluster differently in each direction at small scales, but average over large enough distances and the density should even out. This isotropy is fundamental to how we model cosmic expansion and evolution. The Hercules Corona Borealis Great Wall violates this assumption directly. It creates a massive density enhancement along one specific line through space. Point a telescope toward the Great Wall and you see far more matter than average. Point 90 degrees away and you see less. The universe demonstrably does not look the same in all directions when you include structures this large. Some cosmologists argue this does not truly break the cosmological principle, because the principle only needs to hold when averaged over scales larger than the largest structures. If the Great Wall represents the biggest thing in the universe, then averaging over scales of 20 billion light-years or more should restore uniformity. The problem is we cannot observe scales that large. The observable universe only extends about 46 billion light-years in any direction from Earth. This limitation means we can never test whether the cosmological principle holds at scales larger than the structures we observe. We assume it does, based on theoretical arguments, but we have no direct evidence. The Great Wall forces us to question this assumption. If structures 10 billion light-years across exist, what prevents structures 20 billion light-years across from existing, or 50 billion light-years across? The observable universe might be too small to capture the universe's true large-scale structure. We could be living in a region that appears smooth at scales we can measure, but actually sits within much larger structures we cannot see. This would be like trying to understand Earth's geography by examining a square mile of Nebraska. You might conclude the planet is flat grassland, stretching infinitely in all directions. You would be wrong, but you would have no way to know. The alignment of large structures suggests preferred directions might exist. The axis of evil in the cosmic microwave background radiation aligns with other large-scale features. The Shapley concentration, the Great Attractor, and several galaxy filaments show correlations in their orientations. These patterns could be coincidences, or they could indicate the universe has large-scale structure affecting everything within it. If the universe has preferred directions, many cosmological calculations become invalid. The equations describing cosmic expansion assume expansion is the same in all directions. They assume no center, no edge, no axis. Preferred directions would mean the universe expands faster in some directions than others. Galaxies would age at different rates, depending on their location and orientation. The cosmic history we have reconstructed from observations might be correct for our local region, but wrong as a description of the universe as a whole. This possibility opens uncomfortable questions. Where is Earth in this larger structure? Are we in a typical region or an unusual one? Do the physical constants we measure here apply everywhere? How much of our cosmology is local knowledge mistakenly applied universally? The Great Wall suggests we might be asking the wrong questions about the universe because we cannot see enough of it to ask the right ones. Next-generation telescopes will map the universe with unprecedented depth and coverage. The James Webb Space Telescope, already operating, peers deeper into space and time than ever before. Ground-based observatories, like the Vera Rubin Observatory, will survey the entire visible sky repeatedly, cataloging billions of galaxies and tracking how they evolve. The Square Kilometre Array will map neutral hydrogen across cosmic history, revealing structure in regions too distant for optical surveys. These instruments will specifically search for more structures, like the Hercules Corona Borealis Great Wall. They will map gamma-ray bursts with better precision. They will survey larger areas of sky to greater depths. They will measure redshifts for millions of additional galaxies, building three-dimensional maps of cosmic structure back to when the universe was younger than 2 billion years old. If more Great Walls exist, these telescopes will find them. If the original Great Wall is unique, that uniqueness will become apparent as surveys cover more of the observable universe without finding similar structures. Either outcome teaches us something fundamental about how the cosmos works. The observations will also test specific predictions. Modified gravity theories make detailed forecasts about how structure should appear at different distances and scales. Dark energy models predict specific patterns in how galaxies cluster. Alternative cosmologies suggest different distributions of voids and filaments. Next-generation surveys will have enough statistical power to distinguish between these possibilities. One critical measurement involves the cosmic microwave background radiation at higher resolution. Current maps resolve temperature fluctuations to about 5 arc-minutes, roughly 1/6 the width of the full moon. Future missions might achieve resolution 10 times better. This would reveal smaller scale patterns that could indicate the seeds of structures like the Great Wall. If those seeds do not appear in the background radiation, it definitively rules out the Great Wall forming from initial density fluctuations. Gravitational wave astronomy adds another tool. Future space-based gravitational wave detectors will sense mergers of supermassive black holes across the observable universe. These black holes sit at the centers of massive galaxies, which concentrate in structures like the Great Wall. Mapping black hole merger rates in different regions of space tells us how galaxy density varies at cosmic scales. High merger rates would indicate dense structures. Low rates would mark voids. The telescopes will also track cosmic expansion more precisely by measuring distances to many more supernovae and other standard candles. This improves our understanding of dark energy and how it evolved over time. If dark energy variations contributed to forming the Great Wall, better measurements should reveal patterns in expansion rates that correlate with large-scale structure. Surveys will map the distribution of dark matter using gravitational lensing. Massive structures bend light from background galaxies in measurable ways. By analyzing millions of lensing events, astronomers build maps showing where dark matter concentrates. These maps will reveal whether dark matter forms structures as large as the Great Wall, or if the Great Wall is primarily normal matter distributed unusually. Perhaps most importantly, Next-generation telescopes will observe the universe at epochs we have barely explored. They will see the first billion years after the Big Bang in detail, watching how the earliest structures formed. If the processes that created the Great Wall operated differently in the early universe, these observations will show us how. We are entering an era where observations will outpace theory. Telescopes will find things we have not predicted. They always do. The universe began in a quantum state. At the moment of the Big Bang, everything was so small and dense that quantum mechanics governed its behavior. Tiny quantum fluctuations, uncertainties in the position and energy of particles, existed throughout this primordial state. Then cosmic inflation occurred. Space expanded exponentially fast, stretching these quantum fluctuations from subatomic scales to cosmic dimensions. These stretched fluctuations became the seeds of all structure. Regions where quantum uncertainty created slightly more energy turned into slightly denser patches of space. When inflation ended and normal expansion resumed, these density variations remained frozen into the fabric of space. Gravity then spent billions of years amplifying them into galaxies, clusters, and the cosmic web. We can still see these quantum seeds today. They appear as temperature variations in the cosmic microwave background radiation. The pattern is random, as expected from quantum fluctuations, but it follows statistical rules determined by the physics of inflation. Analyzing these patterns tells us about conditions during the first fraction of a second after the Big Bang. The connection between quantum fluctuations and large-scale structure is one of cosmology's greatest triumphs. We can trace the history of specific galaxy clusters back to quantum events happening when the universe was 10 to the power of minus 35 seconds old. The mathematics works. The predictions match observations, except for structures like the Great Wall. Quantum fluctuations during inflation should create density variations with a maximum size determined by how long inflation lasted. Inflation probably continued for about 10 to the power of minus 32 seconds. This duration limits the size of fluctuations to scales that grow into structures no larger than about 1.2 billion light-years. Longer inflation would create larger fluctuations, but observations of the cosmic microwave background radiation constrain how long inflation could have lasted. Some physicists proposed that inflation might not have been uniform. Perhaps different regions of space inflated for different amounts of time. Areas that inflated longer would have larger quantum fluctuations stretched to bigger scales. These regions could produce larger structures like the Great Wall. The challenge is explaining why inflation would vary without conflicting with the uniformity we observe in the cosmic microwave background. Another idea involves multiple fields during inflation. Standard inflation models use a single quantum field to drive exponential expansion. Models with multiple fields can create more complex fluctuation patterns. These patterns might include rare, exceptionally large variations that seed megastructures. The mathematics becomes complicated quickly, and most multiple field models have been ruled out by observations. A more exotic proposal suggests the Great Wall might not come from quantum fluctuations at all, but from cosmic strings or other topological defects. These are hypothetical structures that might have formed during phase transitions in the very early universe, similar to cracks that form when water freezes. Cosmic strings would be linear defects threading through space, potentially seeding the formation of linear structures like the Great Wall. No evidence for cosmic strings has been found despite extensive searches. They should leave specific signatures in the cosmic microwave background radiation. Those signatures are absent. This does not completely rule out cosmic strings, but it makes them unlikely as an explanation. The quantum connection remains our best framework for understanding how structure forms, even if we cannot yet explain the Great Wall within it. The universe will continue expanding forever. Dark energy ensures this. As space expands, dark energy's repulsive effect grows stronger because its density remains constant while gravity from matter dilutes. Eventually, dark energy will dominate completely. Expansion will accelerate until galaxies beyond our local group recede faster than light, disappearing beyond an event horizon we can never cross. In about 100 billion years, the night sky will look very different. Most galaxies visible now will have moved beyond the observable universe. Stars will continue to form from remaining gas, but the gas supply is limited. Star formation will peak, then decline. After about 1 trillion years, no new stars will form. Existing stars will age and die. The universe will enter a dark era dominated by stellar remnants, black holes, and dark energy. The Hercules Corona Borealis Great Wall will play a role in this future. Its enormous gravitational mass will hold the structure together even as space expands around it. Galaxies within the Great Wall will merge over billions of years, forming larger and larger galaxies. Eventually, the entire structure might collapse into a single massive elliptical galaxy containing quadrillions of stars. Or perhaps a cluster of supermassive elliptical galaxies gravitationally bound together. This process depends on whether dark energy remains constant or changes over time. If dark energy strengthens, it could eventually overcome even the gravity of structures like the Great Wall, tearing them apart. This scenario, called the Big Rip, would end with every bound structure in the universe disintegrating, including atom. If dark energy weakens, gravity might regain dominance, potentially reversing cosmic expansion in a big crunch. Current observations suggest dark energy is likely the cosmological constant, remaining forever at its current strength. This leads to the heat death scenario, where expansion continues forever, entropy increases toward maximum, and the universe ends in a cold, empty, dark state. Structures like the Great Wall would be islands of matter in an exponentially growing void. But the Great Wall's existence questions whether our understanding of dark energy is complete. If dark energy varies in space or time in ways that allowed the Great Wall to form, those variations might affect the universe's ultimate fate. Perhaps dark energy is not truly constant. Perhaps it oscillates or follows cycles we have not detected because we have only observed for a tiny fraction of cosmic history. The structure might also affect local regions of space far in the future. Its gravitational influence will reshape trajectories of galaxies for hundreds of billions of years. Galaxy clusters moving through nearby space will be deflected by the Great Wall's mass. This could lead to unusual concentrations of matter or unexpected void formations far from the structure itself. On the longest timescales, even black holes evaporate through Hawking radiation. After 10 to the power of 100 years, no black holes remain. The universe contains only photons, neutrinos, and possibly dark matter particles. The pattern of large-scale structure, including the Great Wall, will have dissolved completely, leaving no trace it ever existed. Yet during the universe's Middle Ages, the era when stars shine and galaxies cluster, the Great Wall stands as testament to processes we do not fully understand, a cosmic monument to the limits of our knowledge. The Hercules Corona Borealis Great Wall exposes cracks in cosmology's foundation. Every aspect of its existence challenges something we thought we understood. Its size violates theoretical limits derived from well-tested physics. Its formation timeline seems impossible given the universe's age. Computer simulations cannot recreate it. No modification to standard cosmology explains it without creating other problems. This does not mean cosmology is wrong. Our models work remarkably well for nearly everything we observe. They predict galaxy formation, cosmic expansion, the cosmic microwave background radiation, the abundance of light elements, and countless other phenomena with stunning accuracy. Cosmology ranks among humanity's greatest intellectual achievements. We have traced the universe's history from fractions of a second after the Big Bang to the present day. But the Great Wall tells us our models are incomplete. Something fundamental is missing from our equations. We might not understand gravity at cosmic scales as well as we think. Dark energy could be more complex than current models allow. Initial conditions in the early universe might have properties we have not discovered, or entirely new physics operates at scales we are just beginning to explore. The scientific method thrives on anomalies, like the Great Wall. When observations conflict with theory, we have two options: reject the observations if they prove faulty, or modify the theory to accommodate them. The Great Wall has survived repeated attempts at rejection. Multiple independent datasets confirm it exists. The measurements are solid. This leaves us with the harder task of modifying theory. History shows this process is not smooth. When Mercury's orbit disagreed with Newtonian gravity, physicists eventually needed general relativity to explain it. When galaxies rotated too fast, we eventually needed dark matter. When the universe accelerated unexpectedly, we eventually needed dark energy. Each discovery forced us to expand our understanding. Each seemed impossible until it became accepted fact. The Great Wall might be signaling the next revolution in cosmology. What seems impossible now, a structure 8 times larger than theoretical limits, might become the key to deeper understanding. Perhaps we will discover new properties of gravity. Perhaps we will find that dark energy has structure and variation. Perhaps quantum effects at cosmic scales are more important than we realized. Or perhaps the answer will surprise us completely. The greatest discoveries often come from directions nobody predicted. Asking why the Great Wall exists might lead us to insights having nothing to do with structure formation. Science works through unexpected connections. A question about planetary orbits led to relativity. A question about galaxy rotation led to dark matter. A question about cosmic expansion led to dark energy. What will the question about the Great Wall lead us to discover? We know the limits of our cosmological models now. Those limits sit at 1.2 billion light-years. Everything larger pushes into territory our physics cannot explain. The Great Wall sits at 10 billion light-years. Between these numbers lies an entire frontier of unknown physics waiting to be explored. The structure exists, that is certain. It demands explanation, that is equally certain. And somewhere in the gap between what we observe and what we can explain, the next revolution in understanding the universe awaits. The Hercules Corona Borealis Great Wall breaks the rules because the rules need breaking.